My name is Jamot and I work as a process engineer for Alfa Laval's energy division. Today I will talk about how we can reduce emissions and save energy in industry by recovering waste heat. It is estimated that between 20 to 50% of industrial energy input is lost as waste heat in the form of exhaust gases, cooling waters, and heat lost from equipment surfaces and heated products. Given this background, waste heat recovery poses a significantly untapped resource for saving energy and reducing emissions. So let's start with where in industry we find the biggest opportunities for recovering waste heat. First of all, we have different types of cooling processes, and in most industrial processes, some type of cooling takes place. And most often, it is just cooled off to the environment. It could be in cooling towers or cooling waters to rivers and seas or in chillers. Secondly, we have exhaust gases and hot flue gases leaving the plants after a combustion process. We could also recover heat by optimizing our processes. And here we need to design processes from the first place with energy efficiency in mind. It could, for example, be around feed effluent interchangers, where a hot output from a reactor preheats the incoming feed. It could be by increasing the number of effects in an evaporation system, and by that we reuse the steam one extra step, or we can optimize around air compressors or steam and hot water boilers. But it is not enough to just have the waste heat available. We must be able to have a need for it in order to actually recover it. So what can we use recovered heat for? First of all, we can use it for integration somewhere else in the plant. And here, replacing steam as a heating media in another process is the most optimal one if the temperature of the waste heat is high enough. We could also preheat boiler feed water, or for example, combustion air or a reactor feed. And here, waste heat of a bit lower grade could be used because lifting the temperature just a bit could also mean energy savings. We can increase preheating in interchangers, or we could use it for some other internal purpose, such as preheating or heating office spaces or showers for our locker rooms. If that's not possible, there is also the opportunity to export and sell the heat. And here we could, for example, export it to a neighboring industrial site, which could use it for some of these purposes I just listed. Or we could export it to a district heating network, of course, depending a bit on the geographical location of the industry. Or we could also export it to some other more niche purpose, such as a fish breeding farm or a greenhouse. If that's not an opportunity either, there are a number of different transformational technologies in which we could use waste heat. One example is in heat pumps. And here we take low-grade heat, and by some input of electricity, we lift it up to a higher temperature where the possibilities for reuse is much higher. We could also use waste heat in an organic Rankine cycle, and by that we produce electricity from waste heat. And that's a system that is a little bit like a same principle as a steam turbine cycle, but instead of steam water, we use an organic media as a working media, and the waste heat is used in the boiling and evaporation process. We can also use waste heat in freshwater generators, where we create high-quality fresh water from seawater in an evaporation process where we utilize waste heat. And this is especially interesting in areas where fresh water is a scarce resource, or in industries where we have waste heat available and there is a need for this type of high-quality processed water. That's often the case, for example, in power plants. We can also use waste heat in absorption chillers, and here we actually provide cooling by utilizing waste heat in a system instead of a compressor. Now we know where to find the heat and what we can use it for. So how do we ensure that we make the most out of the recovered heat? Well, one crucial aspect when selecting the technology for heat recovery is the heat exchanger. And by selecting heat exchanger technology with a close temperature approach, we ensure that we keep as high grade of waste heat available also for reuse. In this example here shown in the picture, we have an industry with waste heat available at 90 degrees, and the temperature approach is just 2 degrees Celsius. This industry exports heat via an intermediate loop, and that's quite common to have an intermediate loop to connect the use and the supply of heat, both to ensure interdependence and to cover the distances between the two sites. And here it's exported to a district heating network, for example. And by having just these 2 degrees temperature approach, we ensure that we keep as high temperature as possible available for reuse. If we instead look at this picture, we have a temperature approach of 8 degrees. And here we can see that the heat available for reuse is much lower. And in this case, if it would have been for a district heating network, for example, it would hardly be possible to reuse it at this level. This principle with the close temperature approach and the benefits it brings, it's also true in other cooling and heating applications where we can, for example, have the opportunity to switch to a lower grade utility. If we have a cooling duty where we today need to use chilled water, so very cold water, it could be possible to switch to a cooling water, for example, or in a reboiler, it could be possible to switch to a steam of a lower pressure. And both these situations means switching to a less energy intensive utility and also most likely a cheaper one. It's also beneficial if we have preheating in interchangers. If we have a close temperature approach, we maximize both preheating and cooling. To estimate the type of savings that we can get from a waste heat recovery system, we have developed calculator tools. And what you see on the screen now is the results page from such a calculator. Here I have used an example where I've inputted figures for an industry with waste heat available at 90 degrees Celsius, where it's to be cooled down to 50 degrees Celsius. They are now reusing this heat for some other heating purpose, and thereby they avoid using steam that would otherwise be produced by a natural gas-fired boiler. In this example, we have savings in energy of 78,000 megawatt hours per year, corresponding to 15,000 tons of carbon dioxide reduction in emissions every year, and annual savings of almost 2 million euros. The payback time is only 9 months here in this example, and that's quite common. We typically see less than 2 years payback time for waste heat recovery systems, which shows that in this example we would have both an environmentally and energy efficient investment as well as a profitable one. The savings that we saw in the previous slides, they come from a number of different points that we can, values that we can bring with waste heat recovery systems. So maybe the most obvious one is that we can save fuel or that we can sell heat. And by that we can also reduce carbon dioxide emissions. And reduction in carbon dioxide emissions is of course most and foremost an environmental benefit, but it could also mean a monetary value if the industry is operating under an emission trading scheme. We will also reduce cooling water consumption, and that means saving resources, but also saving money since we don't have to pay for makeup water, treatment chemicals, pumping power, and so on. It may also mean that we can debottleneck an industry which have reached their cooling capacity limit in summertime, which is not so uncommon. And finally, it could be possible to actually reduce or avoid capital investment in new utility systems, such as cooling systems or boilers. So let's finish up with the short summary. Where do we find the biggest opportunities for waste heat recovery? It's in cooling processes and exhaust gases, and by optimizing our processes. What can we do with the recovered heat? We can use it for direct integration into the plant. We can export or sell the heat, and we can use different number of transformational technologies. And how do we ensure that we use the waste heat most efficiently? Well, a crucial aspect of heat recovery is that we maintain as high temperature as possible. And this can most efficiently be done by plate heat exchangers to keep a close temperature approach. Thank you for watching, and now the chat is open for questions.
My name is Sarah.
My name is Jenny. I'm an energy hunter.